You're here because you want to master the electrolytic cells with the University of Cambridge graduate. This is actually part 2 of our electrochemistry chapter. If you want to watch the previous video talking about electrochemical cells, do take a look at our playlist below so that you can watch the previous video. Hi, I'm Brendan and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. We're going to talk about a new form of cells called electrolytic cells. These are different from electrochemical cells. One main difference that you can see is that there is batteries inside this electrolytic cell. In the name electrolytic, electro means electricity and lytic means break. So here, it is actually the opposite of electrochemical cells. You're using electrical energy to break down chemical substances or promote chemical reactions. Let me teach you how to identify what kind of reactions are happening inside an electrolytic cell. This is important because we need to know what is going on inside the electrolytic cell so that we can answer our exam questions accurately. Step 1, we want to look at the batteries. The polarity of the batteries can be determined by which side is longer and which side is shorter. The longer side is the positive charge and the shorter side is the negative charge. The electrode that is connected to the longer side will be the positive electrode, while the electrode connected to the shorter side would be the negative electrode. This matters because you can tell which side is the cathode and which side is the anode already based on which side of the battery it is connected to. If it is the positive electrode, it will attract negative ions, which are anions. In other words, this positive electrode is also called the anode, whereas the negative electrode will attract positive ions, which are also called cations. And from there, you know the name of this electrode has to be the cathode. Once you have identified which is the cathode and which is the anode, remember our acronym from the last video as well. Anode is where oxidation happens because of NOx. And at the cathode is where reduction happens because of red cat. With that said, we can tell that at the reduction electrode, which is the cathode, this is where there will be a gain in electrons, and at the anode is where oxidation happens. That is where there will be a loss of electrons. Actually, all that I've mentioned is step 0 of identifying reactions. If you want to identify specific reactions happening in the electrolytic cell, you're going to need to follow the following steps. Step 1, you want to first look at the ions and molecules in the electrolyte. So this will require looking closely at the state of the electrolyte. Is this molten or is this aqueous? If it is molten, that means the electrolyte is in a liquid form instead of an aqueous form, which will also mean there is no water involved. With no water, you only have the ions mainly in liquid form to be electrolyzed. This will also mean the molten electrolyte has no H+ and OH- ions because there is no water. Unless, of course, the electrolyte itself has the H+ ions or OH- ions. Next, step 2, you want to look at the potential ions and molecules at each of the electrodes. So if you look at the cations are going to move towards the cathode. And from there, using the ease of discharge table or the reactivity series table, you should be able to tell which ion will win in the discharge battle. In other words, which ion is going to be easier to discharge. Next, we have to look at the anions. The anions are going to go to the anode, and you have to memorize this ease of discharge table for the anions. The anion that is easier to discharge will win the discharge battle and will have the reaction that happens in the electrolytic cell. Once you've sorted out which cations and which anions go to which electrode, you also want to take note of the concentration of the solution. Usually, concentration will only matter for the anode because it only concerns your anions. If you look at the anion table for the ease of discharge, usually for your halogens, which is your F-, your Cl-, your Br-, when they are in higher concentrations, they can oxidize more favorably. You can tell because from the ease of discharge table, let's say it's a concentrated solution, your F-, Cl-, Br-, or even I- will be easier to discharge compared to your OH-. So in a concentrated aqueous solution, these halogens will usually win the discharge battle. As a rule of thumb, your large anions or your complex anions, like your nitrate ions or your carbonate ions, these at a higher concentration is not enough for it to be oxidized. Another consideration is you have to look at the nature of the electrode. If it is an inert electrode, like graphite or platinum, the electrode will not be involved in the reaction. However, if it is an active electrode, they can usually participate in the reaction. And these metals will usually be favored to be oxidized. For example, if you use an electrode like magnesium, this magnesium electrode is going to be much more favorably oxidized compared to your anions being discharged. And hence, the magnesium electrode would be oxidized and shrink in size. Next, let me run through a sample interpretation of an electrolytic cell. So first of all, I'm going to look at the polarity of the batteries. Here we see the longer side is the positive charge and the shorter side is the negative charge. So the electrode connected to the longer side is the positive charge and the electrode connected to the shorter side is the negative charge. So here we can tell that this is actually the anode and this is the cathode. And the anode will have oxidation that happens because of NOx, and the cathode will have reduction that happens. Next, we can look at the electrolyte. The electrolyte is dilute aqueous potassium chloride, and this is dilute. So I take note of the concentration. So we are going to next find out the ions or molecules inside this electrolyte. Here we have K+, Cl-, H+, and OH- because it's in a dilute aqueous form. And now we're going to sort out the cations and anions to their respective cathodes or anodes. So the cathode will have the cations, this will have K+ and H+, and your anode will have Cl- and OH-. Next, we look at the ease of discharge table. In the cathode, H+ has an easier time to discharge, versus in the anode, the OH- will have an easier time to discharge. Because of this, we can write the half equations right now. So your H+ is going to be reduced to form H2 gas, and your OH- is going to be oxidized to form O2 gas. Don't forget your electrons as well and state symbols. Sometimes exam questions will ask you to balance both the half equations and form a complete equation. To do this, we need to make sure that both equations have the same number of electrons. So we need to times 2 to this left one over here. And if you combine them, you actually get 4H plus 4E minus plus 4OH- to give 2H2 plus O2 plus 2H2O plus 4E minus. If you balance this out, you cancel out the electrons and you combine the H plus and OH minus because it forms H2O, you will actually get an overall equation of 2H2O and it gives 2H2 plus O2. So this is the overall equation of the reactions that are happening in this electrolytic cell. Next, let's go through another example interpretation of this electrolytic cell. In this case, this is actually an application of electroplating, and you'll come to see why soon enough. Here, we want to identify the positive terminal and the negative terminal, so we know which electrode is the positive and which electrode is negative. Since the left side is positive, we can tell that this is actually the anode, and the right side is the cathode. So the left is where oxidation happens, and the right is where reduction happens. Next, we want to look at the ions and molecules inside this electrolyte. Here, this is aqueous copper 2 sulfate. So there are Cu2 plus ions, SO4 2 minus ions, H plus ions, and OH minus ions because there is water inside. and now we're going to sort them out. So that at the anode, this is where your SO42- and your OH- will go, and at the cathode, this is where your Cu2+ and your H+ will go. If you look at the ease of discharge table, your OH- will win because complex ions don't usually get oxidized, and your copper-2+ will win because your copper-2+ is easier to discharge than your H+ ion. Afterwards, we can craft the equations for the cathode and the anode. So for the anode, the OH- is going to be oxidized. Let's write some state symbols here because it's a half equation. Don't forget your electrons. And at the cathode, your copper-2+ will win. So copper-2+ will be reduced to copper metal. And because your copper metal is being produced at the cathode, it's actually plating the iron object over here. So your iron object will be covered in copper deposits all around. This is why this is also called an electroplating reaction. We might have to form a balance equation. To do this, we have to make sure that the electrons are balanced. In this case, we might need a ×2 to this cathode over here. And if you combine them, this will simply be 4OH- plus 2Cu2+ aqueous, and this will give you 2H2O plus O2 gas plus 2 copper solid. Last one, I'm going to teach you how to interpret an electrolytic cell when it is a concentrated solution. But it does follow the following simple steps. First, you have to find out which is the anode and which is the cathode. In this case, they already tell you, so you do not need to know. Next, you have to look at the electrolyte. This is concentrated aqueous sodium chloride. So it is concentrated. Again, it does have Na+, Cl-, but also has H+ and OH-. Now we're going to sort out the ions. When we sort them out, the anode will have Cl- and OH-, and the cathode will have Na+ and H+. Based on the ease of discharge, we can tell that the cathode will have H+ that is easy to discharge. At the anode, however, in a dilute solution, OH- will win. But in a concentrated solution, remember, your halogens will typically win. So your Cl- is going to win. When we construct our half equations, we can then find out that Cl- will be oxidized. And you'll produce chlorine gas. While at the cathode, H+ will win and it'll be reduced. And this will produce H2 gas over here. If you look at this diagram, it also tells you that aqueous sodium hydroxide comes out as a product. And sometimes questions will ask you why sodium hydroxide will come out, or sometimes they'll ask you what is the product of this whole electrolytic reaction. For this, you can just look at the ions that are remaining. Na+ and OH- did not get electrolyzed, so if you combine them, that's what will form your sodium hydroxide product afterwards. If you look at a balanced equation, you are actually just using HCl aqueous, and this is being electrolyzed to form Cl2 gas plus H2 gas. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.